Okay, hi everyone, welcome back to this live stream for Windows Server 2003. So I just want to share my screen. Okay, what VPNs do. At any point, two parties can create a connection over the internet. The idea behind a VPN is that you can use these connections to let two parties establish an encrypted tunnel between them using the internet as a transportation medium. The VPN software on each end takes care of encrypting the VPN packets as they go. When they leave one end of the tunnel, their payloads are encrypted and encapsulated inside regular IP packets that cause them to be delivered to the remote machine. Figure 7.2 shows one way to conceptualize the process. As an example, let's say you're in a field at a client site. As long as you're somewhere that your ISP serves, you can dial into the client's local point of presence and get connected to the internet. At that point, you can open a VPN connection back to the servers at your office and do whatever you could do when sitting in front of a normal desktop machine. VPNs and Windows Server 2003. Windows Server 2003 includes support for the Microsoft proprietary point-to-point tunneling protocol (PPTP) and Cisco Layer 2 tunneling protocol (L2TP). L2TP provides a more generic tunneling mechanism than PPTP when combined with IPsec. L2TP also allows you to establish VPNs using a wide range of non-Microsoft hardware and software products, including routers and access devices from companies like Cisco, Red Creek, and Nortel. There are some worthwhile features included in Windows Server 2003's VPN support, including the following. You can set up account lockout policies for dial-up and VPN users. This capacity has existed for network and console users for some time. The Extensible User Authentication Protocol (EAP) allows Microsoft or third parties to write modules that implement new authentication methods and retrofit them to fielded servers. One example of EAP is the EAP TLS module that implements access control based on smart cards and certificates for VPN and dial-up users. If you're using Active Directory in native mode, you can use remote access policies to apply and enforce consistent policies to all users in a site, domain, or organizational unit. These policies can include which encrypted and authentication protocols users may or must use when talking to your servers. How you enable VPN support on your Windows Server 2003 machine depends on whether you're using a server or a client. Client configuration is easy, and you'll see later in this chapter. Just install the dial-up networking service and then use the Make New Connection wizard to create a new VPN connection. On the server side, you'll need to install and configure routing and remote access services and then enable it to accept incoming VPN connections. How VPNs work. The VPN client assumes that the VPN server is already connected to the internet in some way. Here's how a VPN connection process works. 1. The client establishes a connection to the internet, dial-up networking, or any other connection method that can be used for this connection. The client must be able to send packets out to the internet. 2. The client sends a VPN connection request to the server. The exact format of the request varies depending on whether the VPN is using PPTP or L2TP. 3. The client authenticates itself to the server. Again, the exact process varies according to the VPN protocol in use. If the client can't provide valid credentials, the connection is terminated. 4. The client and the server negotiate parameters for the VPN session. This negotiation allows the two ends to agree an encryption algorithm and strength. 5. The client and the server go through the PPP negotiation process described earlier in this chapter. Because both L2TP and PPTP depend on the lower level PPP protocols, you will see why later in section configuring a VPN. Because the contents of the data passed around in steps 2 and 3 vary according to the tunneling protocol in use, let's examine the differences first, though you should understand encapsulation and how VPNs use it to wrap one kind of data inside another. An encapsulation primer. In the beginning, most networks could carry only one kind of data. Each network vendor had its own protocol, and most of the time there was no way to intermingle data using different protocols on the same line. Over time, vendors began to find a way to allow a single network to carry many different types of traffic, resulting in the current assortment of traffic types found on most large networks. However, the internet only works with TCP/IP. If you need to send other types of traffic across the internet, such as IPX or NetBEUI, you can encapsulate it within TCP/IP. Encapsulation works because software at each level of the OSI model has to see header information to figure out where a packet's coming from and where it's going. But the payload contents aren't the most important of these components. By fabricating the right kind of header and prepending it to whatever you want in the payload, you can route foreign traffic types through VPN networks with no trouble. VPNs depend on encapsulation because their security depends on being able to keep the payload information encrypted. The following steps demonstrates what happens to a typical packet as it goes from being a regular IP datagram to a PPTP packet. 1. An application creates a block of data bound for a remote host. In this case, it's a web browser. 2. The client-side TCP/IP stack takes the application's data and turns it into a TCP/IP packet, first by adding a TCP header and then by adding an IP header. This can be called the IP datagram because it contains all of the necessary addressing information to be delivered by IP. 3. The client is connected via PPP, so it adds a PPP header to the IP datagram. This PPP plus IP combination is called a PPP frame. 4. If you are using PPP instead of a VPN protocol, the packet would go across the PPP link without further modification. However, in this example, you are using a VPN, so the next step is for the VPN to encrypt the PPP frame, turning it into unreadable information to be transported over the internet. 5. A generic routing encapsulation GRE header is combined with the encrypted payload. GRE really is generic. In this case, the protocol ID fields in the GRE header says that this is an encapsulated PPTP packet. 6. Now that you have a tag to tell you what's in the payload, the PPTP stack can add an IP header specifying the destination address of the VPN server, not the original host from step 2, and a PPP header. 7. Now the packet can be sent out over your existing PPP connection. The IP header specifies that it should be routed to the VPN server, which can pick it apart and reverse steps 1 through 6 when the packet arrives. So you can see here, figure 7.3, the encapsulation process. Encapsulation allows the use of VPN data inside ordinary IP datagrams, which is part of what makes VPN so powerful. You don't have to change any of your applications, routers, or network components unless they have to be configured to recognize and pass GRE packets, PPTP tunneling. PPTP is a pretty straightforward protocol. It works by encapsulating packets using the mechanism described in the previous section. The encryption step 4 is performed using the Microsoft point-to-point encryption MPPE algorithm. The encryption keys used to encrypt the packets are generated dynamically for each connection. In fact, the keys can be changed periodically during the connection. When the client and the server has successfully established a PPTP tunnel, the authorization process begins. This process is an exchange of credentials that allows the server to decide whether the client is permitted to connect or not. The server sends a challenge message to the client, and the client answers with an encrypted response. When the server gets the response, it can check it to see whether the answer is right. The challenge response process allows the server to determine which account is trying to make a connection. Once it knows that, it can determine whether the user account is authorized to make a connection. If so, the server accepts the inbound connection. Any access control or remote access restrictions still apply. L2TP IPsec tunneling. L2TP is much more flexible than PPTP, but it's also more complicated. It was designed to be a general purpose tunneling protocol, not limited to VPN use. L2TP itself doesn't offer any kind of security. When you use L2TP, you're setting up an unencrypted, unauthenticated tunnel. Doing so over the internet would be dangerous because anyone who wanted to could read your traffic. To address this issue, you can use L2TP in conjunction with IPsec, which was discussed in Chapter 4, Managing IP Security. The overall flow of an L2TP plus IPsec tunnel session looks a little different from that of a PPTP session because IPsec security is different. Here's how the L2TP IPsec combination works. 1. The client and server establish an IPsec security association using the ISA, KMP, and Oakley protocols as discussed in Chapter 4. At this point, the two machines have an encrypted channel between them. 2. The client builds a new L2TP tunnel to the server. Because this happens after the channel has been encrypted, there's no security risk. 3. The server sends an authentication challenge to the client. 4. The client encrypts its answer to the challenge and returns it to the server. 5. The server checks the challenge response to see whether or not it's valid. If so, the server can determine which account is connecting subject to whatever access policies you've put in place. At this point, the server can accept the inbound connection. Note that steps 3 through 5 mirror the steps described for PPTP tunneling. This is because the authorization process is a function of the remote access server, not the VPN stack. All the VPN does is provide a secure communications channel, and something else has to decide who gets to use it. Installing the routing and remote access services. Now that you understand the principles behind dial-up networking and remote access, you can learn how to actually install and configure remote access services on your server. You can configure a Windows Server 2003 computer as either a remote access client or a remote access server, but usually you install the client component on a Windows 2000 Professional and XP Professional computers. Dialing into Windows Server 2003 remote access servers. Windows Server 2003 includes RRAS to support remote access services as a server. RRAS is actually installed by default with Windows Server 2003. However, it's not activated until you run the routing and remote access server setup wizard. Exercise 7.1 will lead you through the process of configuring an RRAS server using the wizard. Installing the routing and remote access services. 1. Open the RRAS MMC console by selecting Start Administrative Tools, Routing and Remote Access. 2. Select the server you want to configure in the left pane of the MMC. Right-click the server and choose Configure and Enable Routing and Remote Access. The RRAS Setup wizard appears. Click the Next button. 3. On the common configuration page of the wizard, select the Remote Access Dial-Up or VPN radio button and then click the Next button. 4. The remote access page appears, allowing you to select a VPN server and or a dial-up server. Check both checkboxes because you will configure a VPN server later in this chapter. Note that VPNs require more than one network interface card, as you will see later. If you don't have more than one interface at this time, then just select the dial-up option. Click the Next button. 5. The Macintosh guest authentication page appears. The Macintosh operating system allows anonymous remote access. If you want your RRAS server to mediate this behavior, click the Allow Unauthenticated Access for All Remote Clients button. Click the Next button. Note that this page will appear only if the Macintosh file and print services are loaded. 6. The IP address assignment page appears. If you want to use DHCP, either a DHCP server on your network or the built-in address allocator, leave the Automatically Radio button selected. If you want to pick out an address range, select the From a Specified Range of Addresses button. Click the Next button. If you choose to use the static addressing at this point, the wizard will give you the opportunity to define one or more address ranges to be assigned to remote clients. Exercise 7.1 continued. 7. The Managing Multiple Remote Access Servers page appears. You use this page to configure your RRAS server to work with other Radius-capable servers on your network. In this case, you don't want to use Radius, so leave the No Use Routing and Remote Access to Authenticate Connection Requests button selected and then click the Next button. 8. The Summary page appears. Click the Finish button to start the RRAS service and prepare your server to be configured. You'll see a message indicating that you'll need to configure the DHCP relay agent. More on that later if you want to forward DHCP messages to another network. Figure 4, the RRAS window as it appears after completing the RRAS setup wizard. Configuring your remote access server. Most of the configuration necessary for a remote access server happens at the server level. In particular, you'll use the server's properties dialog box to control whether the server allows remote connections at all, what protocols and options it supports, and so forth. You also have to configure settings for your users, which you'll read about in the next section. To open the RRAS server's properties dialog box, choose the server you're interested in and select Properties, or right-click the server and select Properties from the context menu. The options in the Properties dialog box are described in the following sections. So I'm going to leave it here today for this live stream. If you like listening, thanks and have a nice day.